The sun sets. 3 hours later, it rises again. 3 hours after that, it sets. You track it across the sky, and the movement is visible. Not the creep of a shadow on a sundial, but the arc of a celestial body racing overhead. The moon hangs in that sky, not as a distant coin of light, but as a looming disk occupying 15 degrees of the horizon, close enough to resolve craters with the naked eye. This was Earth 4.5 billion years ago, spinning so fast that a single year contained not 365 days, but 1,500. The Hadean Eon takes its name from Hades, an appropriate designation for a planet that had just been struck by a Mars-sized body called Theia. The collision wasn't head-on. Theia delivered a glancing blow, scraping along Earth's flank and ejecting a plume of molten debris into orbit. That debris would coalesce into the moon. The impact did something else. It imparted angular momentum. Earth began rotating once every 4 to 6 hours. At the equator, the surface velocity reached 4,000 miles per hour, roughly 4 times faster than today. This speed had consequences. Centrifugal force flattened the planet into an oblate spheroid. The poles compressed inward, while the equator bulged outward by hundreds of kilometers. Gravity at the poles was stronger than gravity at the equator. That gradient pulled cold polar air toward the equator at varying speeds, creating permanent cyclonic bands. From space, Earth would have resembled Jupiter, a world wrapped in latitudinal stripes of storm systems, each band spinning at different velocities. The sky was not blue. The atmosphere contained carbon dioxide, methane, and nitrogen, but almost no free oxygen. Light scattered through this composition differently, tinting the sky orange or reddish, similar to Titan. The sun was fainter than it is now, only 70% of its current luminosity, but the rapid rotation prevented extreme temperature swings. A patch of ground spent 3 hours in daylight and 3 hours in darkness. There wasn't time for the surface to heat up or cool down significantly between cycles. The day-night gradient was minimal. The planet maintained a uniform, chaotic climate rather than stable weather systems. Because the day was 6 hours long and the orbital period around the sun remained the same, the year stretched to approximately 1,500 days. The moon, which had formed just 15,000 to 20,000 miles from Earth's surface, roughly 15 times closer than its current position of 238,900 miles, orbited rapidly. That proximity placed it within the range of modern geostationary satellites. From the ground, the moon didn't look like a celestial object. It looked like a neighboring world. Angular momentum is conserved in a closed system. The Earth-Moon system contains a fixed quantity of this momentum, distributed between 2 reservoirs: Earth's rotational spin and the moon's orbital motion. When the moon formed close to Earth, its orbit held relatively little momentum. The remainder had to reside somewhere. It was in Earth's spin. This distribution was temporary. The moon's gravity pulls on Earth, and because Earth is not a rigid sphere, but has fluid oceans and a plastic mantle, it deforms. The pull creates a tidal bulge, a distortion of water and rock that rises on the side facing the moon and on the opposite side as well. If Earth rotated at the same speed the moon orbited, the bulge would align directly beneath the moon. But Earth was spinning much faster than the moon orbited. The planet dragged the bulge ahead of the moon's position. The bulge has mass. It has gravity. Because it sits ahead of the moon, it exerts a forward pull. The moon, pulled in the direction of its orbit, gains energy. In orbital mechanics, adding energy to an orbiting body raises its altitude. The moon begins to move away. At the same time, the moon's gravity pulls backward on the bulge. That backward pull acts as a brake on Earth's rotation. Rotational kinetic energy is converted into orbital potential energy and dissipated as heat in the oceans and crust. The moon climbs higher. Earth slows down. We can measure this process. Apollo astronauts left retroreflector arrays on the lunar surface. By bouncing lasers off these mirrors, scientists have determined that the moon is currently receding at 3.8 centimeters per year, roughly the speed at which human fingernails grow. The rate was not constant over geological time. When the moon was closer, tidal forces were stronger, but the configuration of the oceans and continents affected the efficiency of energy dissipation. At times, the rate was faster. At other times, it stalled. The moon is stealing Earth's spin. It has been doing so for 4.5 billion years, converting our rotational speed into its escape trajectory. The process is ongoing. It will continue until either the sun expands and destroys the system, or the Earth and Moon reach a state of mutual tidal lock, where both bodies always show the same face to each other and rotate once every 47 days. Physics predicts the lock will require 50 billion years. The sun will become a red giant in 5 billion. Tidal force is not proportional to distance. It follows the inverse cube law. Force scales with 1 over distance cubed. If you have the distance between two bodies, tidal force doesn't double. It increases by a factor of 8. At 1/15th the current distance, the moon's tidal influence on Earth was over 3,000 times stronger than it is today. The mechanism is friction. As the tidal bulge moves across the ocean floor, water rubs against rock. In shallow seas, this friction is intense. In deep oceans, it diminishes. The difference matters because friction is where Earth's rotational energy goes. The kinetic energy of spin doesn't vanish. It converts to thermal energy. The ocean floor heats up. The water heats up. The energy dissipates as warmth distributed through the global ocean system. The Bering Strait provides a modern example. It's shallow, only about 160 feet deep, and narrow. As tidal currents funnel through this bottleneck, friction is extreme. The water churns. Energy bleeds off as heat. Now scale that effect to a global ocean being yanked vertically by a moon 15 times closer. The Hadean Earth likely had a global ocean with scattered volcanic island arcs, similar to Hawaii or the Japanese archipelago. Without large continental masses to interrupt them, tidal waves traveled circumpolarly, building momentum as they wrapped around the planet. Every time the water surged across the ocean floor, friction converted a portion of Earth's spin into heat. The energy budget is lopsided. Most of Earth's lost rotational energy becomes heat. A smaller fraction transfers to the moon as orbital potential energy, the energy that lifts the moon into a higher orbit. The heat dissipates. It warms the oceans. It keeps the mantle hotter than radioactive decay alone would explain. The constant flexing of the crust generated internal warmth, similar to the heat produced by bending a paperclip repeatedly. Tidal heating kept Earth's mantle more fluid and maintained plate tectonics at a hyperactive rate. Volcanoes erupted more frequently. The crust remained semi-plastic longer, delaying the formation of stable continental platforms. The process also depends on resonance. If the natural frequency of the ocean basin matches the frequency of the tidal cycle, the tides amplify. This is why the Bay of Fundy in Nova Scotia experiences tides over 50 feet high. The shape of the bay creates resonance with the twice-daily tidal cycle. The water sloshes back and forth at exactly the right timing, and each tidal push adds energy to the previous one. The result is dramatic amplification. On the Hadean Earth, the 6-hour rotation meant the tidal frequency was very high. Depending on ocean depth and basin geometry, certain configurations would have resonated, supercharging the braking effect. As continents drifted and ocean basins changed shape over billions of years, Earth's rotation would have slowed in fits and starts. When basin geometry drifted out of resonance, the braking effect weakened. The moon's retreat slowed. When new configurations created resonance, the braking accelerated. The deceleration curve was not smooth. It paused. It jumped. It responded to the evolving geography of the planet's surface. Apollo's laser reflectors confirm that the moon is still moving away at a measurable rate. The braking mechanism is still engaged. Every time the tide comes in and goes out, Earth loses a small amount of angular momentum. The moon climbs a few centimeters higher. The process has been running for 4.5 billion years without interruption. Tidal generating force increases with the cube of proximity. At 15,000 miles, the moon generated tides over 3,000 times stronger than the gentle 2-foot swells we experience today. Computer simulations of a Hadean Earth with a global ocean suggest tidal waves between 1,000 and 5,000 feet high. These weren't breaking waves, they were rises in sea level that advance faster than a person could run. Every 3 hours, the ocean surged inland, flooding vast areas, then receded with equal violence. The intertidal zone, the area between high and low tide, stretched hundreds of miles. No coastline was stable. Volcanic islands were scoured to bedrock twice per rotation. The mechanics of the scouring were brutal. As the water wall approached a basaltic island, the leading edge hit first, rushing up the slope at speeds exceeding those of modern tsunamis. The run-up could carry water to elevations far higher than the wave's open ocean height. Any loose sediment, volcanic ash, weathered rock, accumulated dust, was stripped away in seconds. The water didn't stop. It kept climbing until momentum bled off, then reversed. The recession was equally violent. Water drained back toward the ocean, carrying everything it had loosened. The result was a polished surface, black basalt, worn smooth by twice-daily scour cycles. The constant churning deposited layers of conglomerate rock, pebbles and boulders mashed together by the grinding force of water moving at extraordinary speed. These deposits weren't sorted by size the way river sediments are. The violence of the tidal surge mixed everything. Fine silt with fist-sized rocks with car-sized boulders. When the water receded and the debris settled, it formed a chaotic jumble. Geologists call these deposits poorly sorted. They're diagnostic of high-energy environments. The Hadean Ocean created them on a global scale. The tides didn't just move water, they flexed the solid crust. With the moon so close, the ground itself rose and fell by tens or hundreds of meters every few hours. This constant bending generated friction heat. The process is called tidal heating, and it's the same mechanism that keeps Jupiter's moon Io volcanically active, despite its small size and great distance from the sun. On Hadean Earth, tidal heating kept the mantle hotter and more fluid. It prevented the crust from cooling into a stable shell. Volcanic activity was relentless. The crustal flexing had another consequence: seismic noise. The ground was never still. Low-level earthquakes rippled through the crust constantly as the tidal bulge migrated across the planet's surface. These weren't the catastrophic quakes that collapse buildings. They were persistent tremors, a background hum of seismic activity. Standing on Hadean Earth, you would have felt the ground vibrate. It would have been subtle, but unceasing. The planet was always trembling. The soundscape was overwhelming. Wind velocity at the equator reached 4,000 miles per hour, driven by the intense Coriolis effect of the rapid rotation. These weren't winds in the familiar sense. They were permanent hypercanes, atmospheric bands wrapped around the planet like the stripes on Jupiter. The roar would have been constant and deafening. Add to that the crash of megatides surging across the landscape every 3 hours. The water didn't lap at shores. It hammered them. The sound of a 1,000-foot wave hitting a coastline would carry for hundreds of miles. Hadean Earth was an incredibly noisy planet. There were no quiet places. The wind howled, the water roared, the ground hummed. Evidence for this environment exists. Zircon crystals from the Jack Hills region of Western Australia are 4.4 billion years old. Their oxygen isotope ratios indicate they formed in the presence of liquid water. The chaotic tidal environment didn't prevent water from existing, it defined the conditions under which that water moved. The ocean wasn't a calm expanse. It was a high-energy system in constant motion, driven by the gravitational tug of a moon 15 times closer than it is now. The frequency of the tides meant that any given location experienced a complete cycle: flood, ebb, in 6 hours. There was no prolonged period of stability. The landscape was perpetually transitioning between inundation and exposure. Sedimentary layers from this era, where they survive, show rhythmic banding, consistent with rapid tidal deposition. The geological record preserves the barcode of a planet where water advanced and retreated with mechanical regularity every 3 hours for hundreds of millions of years. The origin of life requires polymerization, the linking of small molecules into long chains like RNA or DNA. In pure water, these chains are unstable. Hydrolysis breaks them apart. The molecules need to concentrate, dry out, and form bonds in the absence of water, then rehydrate to mix with other compounds. Laboratory experiments have shown that repeated wet-dry cycles are among the most effective mechanisms for assembling complex organic molecules from simpler precursors. The Hadean tides provided exactly this environment. As the tides tide surged inland, it flooded shallow pools with a mixture of organic compounds delivered by volcanic outgassing and meteorite impacts. When the tide receded, these pools evaporated under intense ultraviolet radiation from a sun unshielded by an ozone layer. The water disappeared, the molecules concentrated, chemical bonds formed. 3 hours later, the tide returned, rehydrating the system and mixing the newly formed chains with fresh material. This cycle repeated every 3 hours, year-round, for hundreds of millions of years. The moon's proximity created a planetary-scale reactor. The same gravitational force that generated the massive tides also provided the rhythmic wet-dry cycling necessary for abiogenesis. The violent environment wasn't an obstacle to life's emergence, it was the mechanism. The Jack Hill zircons confirm that liquid water existed by 4.4 billion years ago. The chemical signature preserved in those crystals proves the environment was wet. The tidal mechanism explains how that water could have cycled through the evaporation and reconcentration needed to build life's molecular machinery. The moon's tidal forcing didn't just churn the oceans, it created the conditions under which the first complex organic molecules assembled into structures capable of replication. The transition from chemistry to biology remains poorly understood. No single experiment has produced life from non-living material, but the wet-dry cycling mechanism addresses one of the fundamental barriers: the need to concentrate and polymerize molecules in a system that constantly shifts between aqueous and dry states. The 3,000 times amplified tides of the Hadean provided this cycling at a scale and frequency unmatched by any other known mechanism. The moon may have been the engine that powered the assembly line of early life. Cyanobacteria appeared at least 3.5 billion years ago. These microorganisms perform oxygenic photosynthesis. They split water molecules, release oxygen, and use the liberated electrons to fix carbon dioxide. Over time, they pumped enough oxygen into the atmosphere to fundamentally change the planet's chemistry. This event, known as the Great Oxygenation Event, occurred approximately 2.4 billion years ago. Photosynthesis requires sustained sunlight. Cyanobacteria need time to activate their photosystems and ramp up production. On a planet with a 6-hour day, the sun rose and set every 3 hours. The bacteria barely had time to begin photosynthesizing before darkness returned. Their oxygen output was minimal. As Earth slowed and the day lengthened, the window of continuous daylight expanded. At some threshold, the production curve shifted from linear to exponential. Recent research from the University of Michigan suggests that this threshold was reached when Earth's rotation slowed past 19 hours. At that day length, cyanobacterial mats had enough sustained sunlight to maximize their photosynthetic activity. The oxygen they produced began to accumulate in the atmosphere rather than being immediately consumed by reactions with surface minerals. The Great Oxygenation Event followed. The timing aligns with the lunar breaking timeline. Geological evidence from tidal rhythmites and stromatolites indicates that Earth's rotation was slowing throughout the Archean Eon. By the time of the oxygenation event, the day had lengthened significantly from its Hadean starting point. The moon's gravitational drag didn't just slow Earth's spin, it created the temporal framework necessary for photosynthetic life to oxygenate the atmosphere. This connection suggests that the moon's influence extends beyond surface conditions. By lengthening the day, the moon allowed life to shift the planet's atmospheric composition. Without the lunar break, Earth might still be spinning at 10 or 12 hours, with 2 short days to allow cyanobacteria to oxygenate the atmosphere efficiently. The moon didn't just stabilize Earth's rotation, it unlocked the biochemical potential of photosynthesis. The process was gradual. Oxygen levels rose, then plateaued, then rose again over hundreds of millions of years. But the initial trigger, the crossing of the 19-hour threshold, appears to have been linked directly to the lengthening day. The moon's retreat was the pacemaker for one of the most consequential biological events in Earth's history. The deceleration of Earth's rotation was not smooth. During the Proterozoic Eon, specifically the period known as the Boring Billion between 1.8 and 0.8 billion years ago, Earth's day length appears to have stalled at approximately 19 hours. For nearly 1 billion years, the rotation rate held steady despite the moon's continued gravitational braking. The explanation involves atmospheric thermal tides. While the moon's gravity creates oceanic tides that slow Earth's rotation, the sun's heat creates atmospheric tides. As the sun heats the atmosphere, the air expands and exerts a drag that pushes ahead of the planet's rotation. This effect accelerates Earth's spin, counteracting the lunar brake. During the boring billion, these two forces, lunar braking and solar acceleration, appear to have balanced. The day length stabilized at 19 hours. This equilibrium eventually broke. The configuration of continents and oceans changed as tectonic plates drifted. The resonance that had amplified the atmospheric thermal tide weakened. The lunar brake resumed dominance, and Earth continued slowing toward its current 24-hour rotation. The stall has implications. It demonstrates that the deceleration wasn't a simple exponential decay. The system experienced periods of stability and periods of rapid change, depending on the geometry of the ocean basins, the distribution of land masses, and the strength of atmospheric tides. The moon's influence was consistent, but the response was variable. Evidence for the stall comes from tidal rhythmites in sedimentary rocks. These formations preserve daily and monthly tidal cycles as thin layers of sediment. By counting the layers, geologists can reconstruct the length of the day at the time the rock formed. Rocks from the boring billion show day lengths clustered around 19 hours, with little variation across hundreds of millions of years. The rhythm was locked. The eventual resumption of deceleration brought Earth to its current 24-hour day. The process is ongoing. The moon is still climbing away. In another billion years, the day will stretch past 25 hours. In 5 billion years, it might reach 30 or 40 hours if the sun doesn't destroy the planet first. The moon's mass is roughly 1/80th of Earth's. Had it been smaller, its gravitational influence would have been weaker. The tidal braking effect would have been insufficient to slow Earth significantly. The planet might still be rotating at 10 or 12 hours per day. At that spin rate, equatorial wind speeds would exceed 300 miles per hour. The flattening of the planet would create gravity gradients steep enough to prevent the formation of complex ecosystems. Life, if it arose at all, would be confined to simple forms capable of surviving in a hyperkinetic environment. Had the moon been larger or formed closer to the Roche limit, the tidal forces would have been even more extreme. Earth might have become tidally locked to the moon within the first billion years, with one hemisphere perpetually facing the satellite. That hemisphere would bake under constant lunar tidal heating and solar radiation. The opposite hemisphere would freeze in permanent darkness. The temperature gradient would drive atmospheric circulation violent enough to strip away any nascent biosphere. The actual moon delivered neither scenario. It was massive enough to exert substantial tidal braking, but distant enough to slow Earth gradually over billions of years. The process was a soft brake, a controlled deceleration that paced the lengthening of the day to match the increasing complexity of life. As organisms evolved circadian rhythms tuned to the day-night cycle, the day lengthened slowly enough that biological clocks could adapt through gene duplication and mutation. The moon didn't just stabilize Earth's rotation, it synchronized the planet's temporal rhythm with the evolutionary tempo of life. This synchronization was not designed. It emerged from the interplay of gravity, friction, and time, but the outcome resembles precision engineering. A 6-hour day in the Hadean provided the wet-dry cycling necessary for abiogenesis. A 19-hour day in the Archean unlocked photosynthesis and atmospheric oxygenation. A 24-hour day in the Phanerozoic allowed the diversification of complex multicellular life, with metabolic cycles and behavioral patterns tied to diurnal rhythms. The moon is still leaving. The theft continues. In the distant future, the day will stretch to lengths incompatible with current ecosystems, but the sun will likely end the experiment before the process completes. The mutual tidal lock that physics demands will never occur. The story that began with a glancing blow from Theia and a frantic 6-hour spin will end incomplete. A transformation that started with violence and slowed to a rhythm that allowed life to emerge, diversify, and eventually look up at the moon and recognize it as the architect of time. The 24-hour day feels eternal. It is not. It is a moment in a 4.5 billion year slide from chaos to stability, a temporary equilibrium in a system still adjusting from the impact that created the moon. We live in the middle of that adjustment, in the brief window where the day is long enough for complex thought, but short enough to feel familiar. The moon gave us that window. It continues to steal our spin, centimeter by centimeter, year by year, pulling away into the darkness, leaving us with the gift of time.